Welcome to Sundar's lecture. This is lecture number 20, and in this lecture we are going to see how to implement full adder using 2 cross 1 max, and we will see decoders, basics of decoders, right? So what are the topics we have seen in the previous class? See, we have started with the multiplexers, right? So what is multiplexer, and we have seen what is 4 cross 1, 2 cross 1, 8 cross 1 multiplexers, and what is the truth table of the multiplexers. And we have also seen what is the logic diagram of the multiplexer, and we have gone to implementing the Boolean expressions using multiplexers, right? So it is very easy to implement the 8 cross 1 multiplexer for 3 input system, but if we go for 4 cross 1 multiplexer for 3 input system, then you have to do some extra logic informations, right? So that is what we have get this logic informations, and we have implemented the 3 input system with 4 cross 1 multiplexer. And we have also implemented this one, right? Implement using full adder using 8 cross 1 and 4 cross 1. See here, we have implemented it with 8 cross 1. 8 cross 1 is very simple. You can directly do these kind of things. But what you can do with the 4 cross 1 multiplexer, that is what we are going to see in this class right now, right? So this is also this 4 cross 1 we have done, right? 4 cross 1 also we have done. But what we will do for 2 cross 1 multiplexer, and what is the idea? See, try to understand now. This one is very simple now. You take the, so this is the truth table, right? This is the truth table of the full adder, and this is ABC, this is sum, and this is now carry. You know these kind of things, right? So in general, this is 2 cross 1 multiplexer. This is a 2 cross 1 multiplexer. I'm just taking it for sum and carry separately. And you see here, this is A now. You don't do anything here. Make it to A, maybe. This is A. This is A. Input is A. And you see now, we will have B and then C separately, B and then C separately, right? We have these two now, and this is sum. Obviously, this is sum. You don't do anything with sum. You don't do anything with sum, and you know this because this is only one input. This is 0 and this is 1. This is 0 and this is 1, which means if A is 0, then this will be selected. If A is 1, then this input will be selected. If A is 0, this input will be selected, and A is 1, this input will be selected. You know these kind of things. These kind of stuffs we have already seen. And now you have only 2 inputs, right? But you have 8 number of combinations here. So what you do, you just take first 4 separately out. You have to get a combination for this one separately, and you have to get a combination for this one separately. That is the whole idea. Try to understand. This is the whole idea. Right, now you try to understand for sum and carry. For sum and then for carry, you have to do separate things to find what we can do. Right? So you just extend this. You can do this one. See here, for sum and then carry, what is the idea? See here, compare now this sum, only this sum with these two. See, A I have done already, no problem for A. Now these are the two inputs, B and C is the 2, 0, 0, 0, 1, 1, 0, 1, 1. And you see the sum output now. What is this one? 0, 1, 1, 0, which means your input are inverted and the output gets 1. If inputs are inverted, your output gets 1. Then what is the combination of this BC and this output sum? It is XOR. It is XOR of BC. Try to understand. It is the XOR of BC, right? So for sum these 4, what you can get now for sum input, these first 4 can be taken as XOR. This is actually XOR, right? And you see this one now. Obviously, this is 0, 0, 0, 1, 1, 0, 1, 1. See, you have to see separately for this. For this one you see separately, for this one you see separately, because we have 2 inputs, right? So this is the first input, and this is the second input of the sum multiplexer. and this is the first input of carry, and this is the second input of carry for the multiplexer. And now you see this one. This is 0 1 1 0, right? So that is what I have written it as XR. And you see this one now 0 0 0 1 1 0 1 1. Again BC is there, and it is 1 0 0 1. What is this one? This is XNOR. This is XNOR. XNOR. And what you can do now? Simply you draw the diagram. Simply you put XR. Simply you put XR. Give input as C and then B. Connect this XR to this one. Very simple, right? And what you do now? You can directly put a NOT gate here so that you will get XNOR. Try to understand what is the B XR of C can be also written, you can write like this, right? So B XNOR of C can be also written as what? B XR of C the whole bar. That is what you are getting here. So what you do, simply you do what? You put a NOT gate here and you connect this one, and then what happens now? Now that's all, we have completed. You will get some output. Try to understand. You give 0 and then 0 0 here. What it will be now? If this is 0 0, then output will be 0. And if this output is 0, then if this is 0, then this 0 will be selected to the output. The output will be 0 for some. Try to understand. You just implement this one by using this. You put 0 0 1 and then 0 0 0 1 0 0 1 1, whatever it may be. You do this one, you will get the sum output here in 2x1 max. Very simply. Right? Now what you have to do? You have to do for carry, right? What will you do for carry? For this input is what? For this input, see this one, you have to see for this one 0 0 0 1. What is this one? This is actually, and again you see A is already given, and you have to see for BC 0 0 0 1 1 0 1 1. What is this one now? What is this output? You try to compare with the gates now, so that it will be very easy to understand. If you are going for n minus 2, which means this is actually you can implement with 8x1 multiplexer, but if you are going for 4x1, then it is very simple. We have seen in the previous class. But even if you are going for 2x1, then you have to compare with the gates. That is the whole idea, right? So if you do so, compare this one. What is the output of this one? Obviously, it is an AND gate. AND gate, right? This is AND gate. AND gate, because all the input, when both inputs are 1, the output goes to 1. So it is nothing but an AND gate. This is an AND gate operation. And you see this one 0 1 1 1. What is this output now? What is this one? See, if one input is 1, then output goes to 1, then obviously it is an OR gate. So this is an OR gate. So what you do now? Very simply, you draw a OR gate, and you just connect this one here. For example, maybe you draw it here because I don't have space. So this OR gate has to be connected to this one. And what you can do here, you can get an AND gate, and what you can do, you just connect it here. So you just give this input. This is for OR gate, this is for AND gate, and you just connect this one, B to OR gate, and this one should be connected here. And now you see this one. Simply, oh, this one I have written sum, right? No, this is carry, this is carry, this is carry. So what you have done, we have just implemented the full adder using 2x1 multiplexer with some gates. It is possible, right? It is possible. Now you just put the values of ABC. Obviously, you will get this one. So you put a box here. That is the combinational logic circuit, right? So we have implemented. Just try to do this one for full subtractor using 2x1 mux, right? You do that by yourself. That is a case study. I have given you idea, right? So we will go for now decoders. Okay, now we have came to decoders now. See, we have seen what is multiplexers and we will see demultiplexers separately. That is very easy if you know what is decoders. Anyhow, see, a decoder is a logic circuit that accepts set of inputs will be there that represents a binary number, which means a binary number inputs will be there. For example, 0, 0, 0, 1, 1, 0, 1, 1, it is a 2 input system. If it is a 3 input system, then it will be 0, 0, 0, 0, 0, 1, 0, 1, 0, whatever it may be, right? That you will have right now. And you see here binary number and activates only the output that corresponds to that input number. Only one output will be enabled, depends on the number of inputs. Right? What is that number of inputs? Is the binary system input. That's all. In other word, a decoder circuit looks at its inputs, determine which binary number presents there. Which means, for example, if you give 0, 0, then the minterm of that one is nothing but it is 0. For example, if it is a three input system, maybe even if it is a 4 input system, 100, what it actually represents, what is the minterm of 100? It is 4. So what it will do, it will activate only the fourth output in the output side if you get that input. That is what here they are explaining you. So it determines which binary number presents there and activates the one output that corresponds to the number. All other outputs remains inactive or it will be 0, right? So in general, a decoder has n input lines to handle the n bits and form 2 power n output lines. See, for example, in decoders, we generally have m number of inputs and n number of outputs. It is not that exactly it is to be happen. It is to be happen, which means we generally use this one now. So n cross 2 power n. We generally use this as a decoder notation, but it is not like that. It should not be like this one. But in general, decoders will be used like this. But it is not limited. It is not restricted to only this form. Try to understand. You don't remember that is only the decoder. No, it is not like that. You have a number of inputs. You will have a number of outputs. But the number of inputs is lesser than the number of outputs. That is the whole idea. Encoder it will be inverted. But I will explain you a bit that also. Right. Right. For example, if you have 1 cross 2 decoder, what this one actually means? See this one. This is the decoder. And I will say, and I will tell you what is inside the decoder. It has one input and it has two outputs now, simply, right? So n is equal to 1 here, that's all. So 1 input and 2 power 1 output, that's all. That is the whole idea. This is 1 cross 2. Then this will be now, maybe if you take this as A and this output, maybe I will put it as D0, D1. Right, what it will do now? What it will do? If A is equal to 0, if I give 0, then D0 should become 1. This will be enabled. That's all. And if A is equal to 1, then D1 has to become 1. And here the D1 will be 0. And here the D0 will be 0. That's all. D0 will be 0. This is the whole idea. Try to understand. This is the whole idea. This is nothing but response 0. This will response to 1. Simply. Right. So that is the whole idea. Now, if you have 2 cross 4 decoder, let me do it very fast now. Because everything is very easy, right? So here we don't have selector switches. Try to understand. That is the only difference. You don't have selector switches. So this one is like this. So what is the n here? N is equal to 2 here. So number of inputs will be what now? It will be 2 inputs. It will be 2 inputs. And how many outputs will be there? 4 outputs. 1, 2, 3 and then 4. Right, now what is this one now? This is D0, this is D1, this is D2, this is D3. And what is this one now? Make it as A and then B. Right, what is this is? What this is 0, 0, 0, 1, 1, 0, 1, 1. Or in other hand, I can write this as A bar, B bar. And this as A bar, B. And this as A B bar and this as AB. which means this is the minterms, right? This is the minterm. This is actually 2 cross 4 decoder. 2 cross 4 decoder. And what is happening around here now? What is happening around here? If this is A, this is B, and what happens to D0, D1, D2, and then D3? What will happen? Now I will make the table. Right now you see I have just made the table, right? If I give 0 0, what it will this will enable this output. That means 0 0. D0 will be enabled. All other outputs will be 0. That is the idea. That is the idea. If I give 0 1, that means this one, it will enable this one now. This one. So D1 will be 1. All other outputs will be 0. Like that, if you enable 1 0, then it will be enabled. Then 1 1, this D3 will be enabled. And what is this one actually? This is nothing but minterm 1. This is minterm 2. This is minterm 3. This is minterm 4. What you can say now, this is actually converting the binary numbers into minterms. So decoder, you can say like it is a conversion of binary number to minterms. This is the A bar, B bar, A bar, B, this is A, B bar, this is A, B, right? What is this one? 0 means bar, you put bar, right? So if it is 3 cross 8 decoder, what it will be now? I will just put the diagram, right? Now you see, this is actually 3 cross 8, right? Decoder. And the idea is now you will have 3 inputs, that means n is equal to 3, so that it will be 3 cross 2 power 3, so that it becomes now 3 cross 8 decoder. Simply, this is A, this is B, and this is C now. And what will be the outputs now? Very simply, this is D0, this is D1, D2, D3, this is D4, this is D5, and this is D6, this is D7 simply. So what you will have now? 0 0 0, 0 0 1, 0 1 0, 0 1 1, this is 1 0 0, this is 1 0 1, this is 1 1 0, this is 1 1 1 simply, right? So what will happen now? If I give 0 0 0, then D0 will be enabled. Try to understand. If I give 0 0 0, D0 will be enabled. And what is the minterm of this one? And you just try to write that one often, because that will help you in converting the smaller decoder to a bigger decoder, right? So what it will be now? Actually, this will be A bar, B bar, C bar, which means this is minterm 0. This is minterm 0. Maybe I will write down all these things. So now you see this one. I have just written, right? So this is the minterms, and it will be enabled. Try to understand. If I give 1 0 1, then minterm 5 will be enabled. Minterm 5, and D5 only enabled. All other outputs will be 0. Simply as this one, right? So I don't need to put like the exact truth table here to explain, because it is very simple to understand too, right? What is inside this decoder? How it is actually working? What is the logic diagram inside the decoder? That you have to understand, right? So what is that? See here, I have just drawn this one. Maybe I will like move this one. See here, this is inside the decoder. This is inside the decoder. Try to understand, right? And what is happening around here? This is the, if I give 0 0 0, then this B bar, this is actually A bar, this is B bar, and this is C bar. These three will be connected to this one, that is 0, which means I have written this as Y0, Y1, Y2. Try to understand. You may write it as D0, D7, right? So anyhow, 0 0 0, this AND gate will be enabled, so all other AND gates will get 0, because this is 1, right? This is 0, this both are 0, then this is 1, means then this C will be 0, and here any 1 will be there. Any one input will be 0 in often in all the other cases of the AND gate, so that only one AND gate will be enabled for each input, that is 0 0 0, then this AND gate will be enabled. This AND gate will get all three inputs as 1. Like that, if you try to do it for the other inputs, that means 1 0 1 means this AND gate will be enabled. And like that, if this is enabled, then output will be 1. So all other output will be 0. That is the whole idea, right? So this is wholly inside the decoder. Try to understand. This is applicable for all other decoders too. 2 cross 4 means there will be 4 AND gates, and then 4 cross 16 means there will be 16 AND gates, right? So this is the general idea. This is the general idea, right? What we will do now, we try to implement the Boolean expressions in decoders, right? Oh, we have done for multiplexers also, right? Like that, we will do this one. So what is this one? They have given you an expression f1 of x0, x1, x2 should be is equal to summation m of 1, 2, 4, 5. Which means what they are saying you, this is a 3 input system and these min terms should become high. These are ones, right? And for f2, it is summation m is equal to 1, 5, 7. And you need to implement this one using the decoder. So how many input system is this one now? It is a 3 input system. Then you go for 3 cross 8 decoder simply, right? So I will put the diagram, right? You see here, I have just taken for both things, Anyhow, 3 cross 8 decoder, I have drawn this one. And these inputs should be high for F1, for the output of F1, and this is the function 2. And what you do, you draw an OR gate, I will explain you bit very easy this one. One OR gate for function number 2, make this function to be F1, and for function 2, you draw another OR gate, simply another OR gate, and you take this as now function number 2, that means F2. And F1 should, what is the min terms should be high? This is 1, 2, 4, 5. So what you can do, you just connect this one, and 2 is there, connect this 2, and then 4 is there, you just connect. So this is very clumsy anyhow. I need to do this one anyhow. I don't have space here, so this should be connected. And for this one, you have to connect this one, and 5, this 5, and this is 7, right? So 7 should be connected. So now what happens? Try to understand. If I give 0, 0, 0, then the output of this is enabled, but I have not connected to this one anywhere. So both F1 and F2 will become 0 for the min term 0. That means input 0, 0, 0. I don't need, right? And if I give 0, 0, 1, then this 1 should become 1. And this one is connected to F1 as well as F2. Both will become now 1 simply. And if I give 0, 1, 0, that is min term 2. That min term, maybe this output, maybe I will write it as D0, D1. We generally write this one, right? D2, this is D3, this is D4, this is D5, this is D6, and this is D7. So D3, 2 will be enabled, and that 2 is connected only to this OR gate. So F1 is enabled, F2 will be disabled. And this is how you can implement. You just try to figure it out for all other inputs. What is happening around for F1 and F2. Very simply, you can do this one, right? This is how you can implement the Boolean expression using decoders. Very simple. And if you go for this one, this is summation m, this is a SOP function, and this is now POS function. POS. And how will you do this one now? What does this one actually means? This is nothing but x0, x1, x2 is the inputs for function number 1, and the min terms 2, 7 has to become 0 for this one. If I give this 0, 0, 0, 0, 0, 1, whatever it may be, for min term 2 and min term 7, it has to become 0. So this is very simple. You put OR gate here, right? Now you put XOR gate, NOR gate. What will you do now? Just try to understand. I will put this. This is one NOR gate. Try to understand. And you put another NOR gate, maybe with a different color. Put another NOR gate. What happens now? You try to do this one. First, you have to connect 2 and then 7. This 2 has to be connected, and then 7 has to be connected, right? So you just connect this 7 to this one, simply this one. And for this is 0, 5, 7. So what you do now? 0, you just take this, maybe I will just do this one. So 7 is here, so straight away you connect this one. and 5 is here, so straight away you connect this one too, and this 0 has to be connected here. Simply, this is a NOR gate, right? To understand. So this is now F1, this is now F2. Simply. So what you do now, you give 0 0 0. What it will be now? We know this one, right? We have already know this is D0, D1, this is D2 output, this is D3 output, this is D4 output, this is D5 output, this is D6 output, this is D7 output. If I give 0 0 0, then this will be enabled, right? So if this is enabled now, this is becoming 1. So this 1 is actually connected to this NOR gate. If you are getting a 0 to this NOR gate, then what happens here? What happens here? If this is 0, then this NOR gate output should be 1. Can you understand? Can you understand? Sorry, this NOR gate. If you get any 1 here, then this output should become what now? It will be 0. So F2 is getting 0. So that is what we have given here. So 0 for 0 0 0, this F2 should get 0. And for 0 0, maybe you get that as 0 1 0, which means what is this one now? What is this one? This is the activation of minterm number 2, that is D2. D2, this is connected to F1 NOR gate. So what happens here? I am getting 0 here, right? So if I get 0 here, then what happens? This, sorry, this, if I get 1 here, this will be enabled, right? So this, if I get 1 here, then F1 should become 0. So if you check it out for any other inputs, even if you do so for all other cases, you just check it out. This F1 and F2 become 0 at minterm number 2 and 7. For this F2 becomes 0 for 0, 5, 7. Try to understand. Thus, we have implemented the Boolean expressions using decoders. Right? This is how you need to do. And we will see what is the decoders with enabled pin and how it will work now. If you have enabled pins, then what is the advantage we can take out from the decoders? For example, you can implement a larger decoder using the smaller decoders if you have enabled pins. That is what we are going to see in the next class. What is the enable pin? And you can also say that it is a demultiplexer. And we will see that interesting topic in the next class. Put the comments in the box, in the comment box. If you have any doubts, you try to ask me, we will discuss, right? So what are all the topics we have seen in this class? See, we have just implemented the full adder using 2 cross 1 multiplexer, right? What we have done now, we have gone for n minus 2. That means we have 8 outputs, 8 input combinations, and that has been implemented using 2 cross 1 multiplexer. Right, so we have done this one, right? We need gates here, we need gates. Without gates you cannot do that one. So the next topic, we have gone for decoders. And what is decoders? We have seen decoders which are nothing but m number of inputs, n number of output, but in general we use n cross 2 power n decoders, right? We have seen what is 2 cross 4, 3 cross 8 decoder, what is inside 3 cross 8 decoder, and we have just implemented the Boolean expressions using decoders. Right? We will see in the next class. Thank you.